Good morning, everyone, and welcome to today's free workshop, an initiative taken by Pat. Today's workshop is going to be focused on risk-based optimization using Python. I'm Abhishek Kaushik, your host for all these free workshops and webinars. I'm delighted to introduce our instructor for this session, Professor Gerhard Kling, who works for the University of Aberdeen. Professor Kling brings over 20 years of rich experience spanning higher education, consulting, and ethics. Before joining Aberdeen, he held professorships at SOAS University of London, University of Southampton, and among other prestigious institutions. He has also worked as a practice specialist in corporate finance at McKinsey & Company, where he focused on firm valuation, mergers, and acquisitions. And what makes Professor Kling particularly exciting as an instructor is his genuine passion for programming. He's fluent in not just one language, but multiple programming languages. To name a few, Python, C, C++, MATLAB, Stata, and much more. In his free time, I got to know that he enjoys recreational programming with tools like Godot, Blender, and Unreal Engine. He is also the director of Unicorn Ltd. And runs a YouTube channel by the same name, offering free data science education to people. You can find all of his extensive work across the GitHub repositories, covering everything from data to machine learning and whatnot. In today's 90-minute session, Professor Kling is going to be teaching us, and we're going to be exploring how to allocate funds across asset classes such as commodities, stocks, cryptocurrencies to maximize returns while minimizing the risk. You'll also learn about the risk trade return trade-off and how to obtain financial data using APIs and how to derive optimal portfolios using Python. Then again, we'll deep dive into the mean variance optimization and risk-based portfolios, including the minimum risk portfolio and maximum diversification portfolio. All the materials, including data and scripts, are available on Professor Kling's GitHub, so you'll have everything you need to continue learning after today. Without further ado, let me hand things over to Professor Kling. Over to you, Professor Kling.
Thank you very much for the introduction. So thanks for hosting us. Thanks for organizing all of it. I have done a few live streams on YouTube in the past, and yeah, it's always I find YouTube live streaming a bit tricky in terms of quality. So I think doing it in Teams and doing a recording is better in terms of the quality, and in particular Wi-Fi speed and so on might be an issue. So at the moment, as you can see, I'm in my home setting. So you might hear in the background my dog barking at one point, so that might happen, which will keep it exciting, I guess. If for any reason there are technical difficulties, I will always do a recording instead. Yeah, so usually my home Wi-Fi is okay, but you never know. If the door rings, it will be an Amazon delivery, I guess. But otherwise, we should be undisturbed. My mobile phone is switched off, so my mother won't bother us, usually. We will see. Yeah, so thank you very much for joining. I also assume a few more people will join while we dive in. So everything is recorded, so you won't miss anything. And there are a few people that can't make it to today's session, and they can, of course, watch the recording. The issue is once I start sharing my screen, which I will do in a minute, I won't be able really to see you. So if you have any questions, just shout out. That would be okay, I guess. You can also use the Q&A function in Teams, or the chat function in Teams. And we can have always a discussion after the session. So usually the plan, I think, is to spend a good hour on the material, and then, of course, have some time at the end for anything you want to discuss. Yeah, I'm more than happy to have a broader discussion around these issues. So I get into it. So in this session, I focus on some practical things, risk-based portfolios using Python. The importance in particular is that in practice, when you actually talk to people that manage assets, nobody seems to use finance theory. They all do different things, and you just wonder why. And the main reason is that finance theory doesn't really work. It's nice in theory. So we talk about stuff like a risk-return trade-off, which is useful. And we also talk about mean variance optimization. So this is what I always cover in portfolio theory at university. But in fact, this is not used an awful lot, and it just doesn't really seem to work. Instead, many people use risk-based portfolios. And somehow we don't seem to talk about this much in academia, but I feel it's really, really important because end of the day, we have to talk about things that people actually can use. Now, to be clear, in this session, I will provide an introduction to it. There is a lot more you can do. I'm also happy to do another session in the future, but I just want to keep it here as an introductory session. There is certainly more, particularly around backtesting, that can be done. So how you make sure that your strategy really works going forward. That can be very, very tricky. And there's a lot more about the optimization processes that certainly can be fine-tuned. So what you will learn in this session is we talk about the risk-return trade-off. It certainly exists. So if people promise you huge returns, you know, like our crypto friends, most likely it also means you take a huge amount of risk. You might not know about it. So there is a certain trade-off. And the idea of portfolio investment is you don't throw all the money into one asset. You try to allocate across assets and you try to optimize the allocation. And we have to discuss that. Now, most importantly, when it comes to optimization for financial assets, you need data. Sadly, in finance, most of the data sources are not for free. So, for instance, you might have access to Bloomberg.
The device already ready to connect.
Oh, yes.
The device pair successful.
Good. So you might have a Bloomberg access. If you don't, you can, of course, try to get Bloomberg, but it's really, really expensive. So I show you a way to obtain data for free using Python, using an API, which is quite handy. There are limitations, I have to say that. We will use Yahoo Finance. The main limitation is Yahoo Finance does not give you real-time access to the data. There is a 15-minute delay. So you can even get high-frequency data on Yahoo Finance, but there is a bit of a time delay, which for trading is a problem. So if you go into high-frequency trading, 15 minutes is forever. So it's not useful for high-frequency trading. But to be honest, this session on portfolio theory is not about high-frequency trading whatsoever. It is for mid and long-term investment strategies. So it's not really suitable for this. If I do high-frequency trading, I don't really care much about these things, to be honest. Yeah, so there are other things I have to consider, which I might cover in other sessions, but it's a very different way of thinking about it. And most importantly, in this session, we talk about risk-based portfolios, why they actually might perform better. We derive the minimum risk portfolio, which you might have already done if you did an undergrad in finance. And then I talk about the maximum diversification portfolio, which is less common. And we look and compare different strategies. I also include the so-called Eigen portfolio. Now, this is something different, which is usually not covered in academic sessions, but again, in practice, many people focus on these Eigen portfolios. So if you have any question, please feel free to shout out. I don't see the chat, so just stop me and we can always have a little discussion. And as I mentioned at the beginning of this session, at the end of today's session, we have definitely about 20-30 minutes to discuss anything you want. I don't want to spend too much time on myself because Python is much more exciting. But just very briefly, I'm mostly an academic, but I do a fair amount of consulting as well. When it comes to My academic background, I'm a mix between economics and mathematics. So I did study both, and in terms of consulting, I mostly focus on fintech, edtech, financial markets, M&A, firm valuation. So that's more or less what I tend to do. In terms of the Python content, I will do a little bit about the Python setup. So this is in particular for people that are not heavy users of Python, because there are different ways to run Python. I then talk about the API using Yahoo Finance, and then we go into the optimization problem. There are many different Python libraries. The best one, in my view, is CVXPY, which is a very, I would say, useful library for all sorts of optimization problems. It's used heavily in finance, but also outside finance, and there is a lot to it. There's also the PyPortfolioOpt, which is another one which does similar things. In my view, it's not as good, but there are pros and cons. So I will focus on the first library, and then I talk about limitations of mean-variance optimization, which basically then trigger the search for alternatives, including risk-based portfolios. And then we dive into different types, and we compare performance, and we talk a bit about backtesting, because this can be very, very tricky indeed. Yeah, and so one should talk about this. Now I just show you my GitHub. So all the slides, all the data is here on my GitHub. So you find here the live sessions, also past live sessions. That's the current one. And you find in the folder live 3 all the scripts. I might do a bit of updating. If anything is missing or unclear, let me know, but you should be able to download this and use it as you wish. Yeah. And of course, as always, feel free to modify and use and reuse this code for your own purpose. You find additional repositories on data science, various aspects of finance, including fixed income securities, simulations, machine learning, and also some stuff on cybersecurity, which again is important in the context of finance and in particular fintech. So you don't have to actually take any notes. Also, the slides, I believe, are online. If not, let me know. I can always put them, and you have it all covered. Now, in terms of how I work in Python, I tend to prefer using a text editor, and I execute my code in the command line. Maybe because I'm old and old-fashioned, I don't know. But I find it more useful, in particular, if I go into serious Python work, where I also need to do testing and so on. I personally prefer that. However, there are alternatives, and it's absolutely fine if you want to use something else. Most people, I guess, would use an IDE, so an integrated development environment, and there are many. There's PyCharm, there's VS Code. There are so many different alternatives, Spider, whatever you fancy, it should be all fine. But in my case, I will stick to Sublime Text. So it's a basic text editor, and I work with the command line. In terms of Python installation, again, if you're totally new to Python, I recommend watching a few videos. I put some links down below about how to install Python and also how to work with so-called virtual environments. Virtual environments are really, really important if you want to control, the packages you use and the versions you use. And this is in particular important if you want to actually develop a software that might run on other machines that might not actually have their own Python installation. So that is a good idea for more serious work. So I tend to use my own virtual environments, and I'll show you how this is done. However, there are alternatives. And I guess most people, in particular the data science people, they use Anaconda, which is great, and it offers more, I would say, compared to a standalone Python installation. So Anaconda already comes with a few options for IDEs. For instance, Spider is already there. PyCharm, I believe, is there. And also RStudio. So if you want to use R, Anaconda already covers this. In Anaconda, you have to work differently with virtual environments. In my case, I create my own and I use the so-called pip installer. Again, if you haven't heard about the pip installer, I have a few videos on that, which you also find on my YouTube channel. So that's my setup, and you will see that in a minute. Our first step is to actually get the data. And of course, if you have access to high quality data from, say, Bloomberg, you can ignore this. You can just use your Bloomberg terminal. It's much better, of course, in terms of quality. But if you don't have any access to data, Yahoo Finance, in my view, is pretty acceptable. And it also covers a wide range of assets. As I mentioned, the only downside is it is delayed by about 15 minutes if you go into high frequency data. In our case, we actually work with daily data. So to be honest, it doesn't really matter because most portfolio optimization problems refer to a mid and long-term strategy. So it's uncommon that within split seconds you keep adjusting portfolios. That is not really meant to be used like this. So we just now dive into a bit of Python. I won't type out the code because it always takes way too long, and some of it can be quite time consuming. But we will talk about it line by line, more or less, and you see actually how this works. And at the end of today's session, we do a little bit of refactoring and thinking about how you can modify code. And I think this is a very nice exercise. Good, let's dive in. So first of all, I have my scripts organized in this folder. I already downloaded some data just as a backup. The issue with APIs is that sometimes these APIs block you, and sometimes they also stop working. In particular, you will discover this when you work with social media APIs. So I work with Reddit. I did a video on how to use Reddit and how to extract data from the notorious Wall Street bets, so data on stock market rumors. And it worked just fine. And then, of course, it stopped working because they changed the API. So APIs are convenient, they're great, but just as a general warning, things can change and you can be blocked. So this is why I also downloaded the data earlier, just in case if it doesn't work. Yeah. So I'm now using, of course, a Windows machine, so it looks a bit different on a Mac operating system. I just type in CMD here, and this should open up my command line. So that's my command line. If you want to create now a virtual environment, you type in Python -m. This is for a module, and then for virtual environment. And then you can name it. You can put any name you like. And this would actually create your own Python installation in this particular folder. I already have done this because that takes quite a bit of time to execute. So we don't want to waste that time. So instead, what I do is I go straight and actually want to now run my Python script. So you would be tempted just to type in now Python and the name of the script. This will cause an error message because we don't yet have our virtual environment active. So when you go to my folder, you see here portfolio. So this is the environment I created. And this environment is basically a Python installation plus all the packages I install. We first have to activate this environment before we can actually run it properly. So you need to do the following. You put the name of your environment, in our case, portfolio. Then you go to scripts. I think for a Mac OS is only script, and then you go to activate. And now you see here that portfolio is shown inside brackets in front of your prompt. Yeah. So this basically means that now we are in this environment. And now you would start doing pip install, and you would install all these different packages like NumPy, Pandas, and so on. I already have done this because, again, it takes quite a fair amount of time. Good. Let's have a little look at our first script. So this is basically our main file. And you notice right away that I organize my work a bit maybe different from what you are used to. I use here two import statements. Yeah, so I write my own functions in portfolio functions. So from portfolio functions, I import data underscore download. So there's a special function I wrote, which I store in a separate script. Now, this is a good idea if you want to also go more into, software development and so on, because for that, you don't want to have everything in one big script. Of course, most academics, I guess, they're not used to this. They threw all of it into one big script, and then it looks like a dog's dinner. Yeah, then you have, thousands of lines of code, and it becomes impossible to debug or to modify. So in my case, I tend to separate my functions and classes, and I then import them when I need them into my main script, and I run this here as my main script. But as I said, it's not always the case that people do it, but I find it better. Yeah, so it's cleaner to do it like this. And then you have another one, which is ticker, where we import tickers. Now, ticker refers to the ticker symbols, and the ticker symbols basically are used to identify securities. Yes, if you are, have done a bit of finance, you will know that companies have ticker symbols. Once you know the ticker symbol, you get access to the data. So when you go to Yahoo Finance and you look up a company, you can identify these tickers. In my case, when you look at my ticker.py, I basically used the Dow Jones Industrial Average, but you can, of course, take any other stock market index or, in fact, any asset, doesn't matter. And I used the tickers based on the composition of the index on the 29th of May last year. Hasn't really changed as far as I know. And you also see I throw in the gold spot price and Bitcoin because both are actually quite interesting. In particular, gold performed really, really well. And I find it kind of interesting to put it in. And of course, Bitcoin, why not? Might be interesting to look into this. In particular, when you now look into risk-based portfolios, the key question is, will you actually invest in Bitcoin to minimize risk? It seems to be a little bit counterintuitive. Now, when you go into this portfolio function script, this is basically where the actual work starts. So in here you have import statements where we import various Python libraries. Of course, Pandas, you will know this if you do some data science and NumPy. And also Y-Finance. Now, Y-Finance is used to interact with Yahoo Finance. So this is the API. And we use that now to download the data. So we define our own function. So keyword def and then data underscore download. The function takes the tickers. We specify it should be a list, but if you're used to Python, this doesn't mean anything. Python does not really enforce it. And then we have to specify the period and the interval. Now, this comes from the Yahoo Finance API. We take here, for instance, the last year, so 1 year of data, and interval, this is basically the frequency of data. We use 1D, which is basically daily data. Now, this is good enough for our type of analysis. And you see we already here assign default values. And you also notice that we specify here strings. Yeah, so that's basically how the API works. And the API will download the data in a particular format, which we then have to modify to get it into a nice pandas data frame. Yeah, so if you have used pandas before, of course, you will know data frame. This is the main object where we store our data. And you see we will return the so-called daily log return of various assets. Yeah, could be stocks, could be commodities, could be anything else. And this bit here, which looks a bit intimidating, is the download function inside the Yahoo Finance API. So that is not done by me. This is done by the API, how it basically behaves. In terms of how the data look like, there are in columns of hierarchies by different tickers. And so it's not straightforward to get from this data format into a data format we can actually work with. For this, I wrote here in line 33, 34, the pandas code to actually get this into a proper pandas data frame. You don't really have to worry much about this. I will just show you the structure. There is also one complexity. So some stocks have normal daily closing prices. So this is basically the price at the end of trading. This is the one we use. Some also might have adjusted closing prices. So sometimes adjustments are done for various reasons. Yeah, so if there's a split, for instance, dividend payments, anything like this, there might be some adjustments. So to accommodate this, I use this if-else statement here to basically permit that in some cases I might use the closing price. In other cases, I might use an adjusted closing price. And then we calculate the log returns. And this is using NumPy. So we refer to MP. The log is the natural logarithm. df is our data frame of closing prices. And then we take a first difference. So if you take the log and then the first difference, you basically are in log returns. And then we drop missing values. We all do this in one line of code. Yeah, of course, you can always separate that, but that's actually quite nice. I quite like this. So this is proper object-oriented programming in real life. And we return then our log return. So that's how this works. And then we import our function. We call the function, and we use the tickers, which refers to the list we specified in ticker.py. And this should download the data. And then we store the data in a CSV file. Now, of course, you can question, why do we use a CSV file? And the answer is, well, because it's easy to read. And I can show you this. I can open the file and you see it. So for human use, CSV files are kind of nice. Of course, we know it's not efficient to store your data using CSV files. In particular, once you get into big data, this won't work. Yeah, there are better ways to store large data, but then you could not easily inspect the data. Yeah, so it's just in our case acceptable because we use daily data. We don't have a huge amount of data, but of course, if you go into high frequency, you have 20 million observations. This would not really work properly. Good, let's just run it and see whether we get some nice error messages. So it's Python, and I call this session 1. .py. And I execute this now in the command line. We are inside our virtual environment. And now it's always a bit like waiting for a train. Now this, of course, means we now interact with the API, and hopefully it's not messing us up. It might mess us up. You never know. Here we go. So it actually did do it. And I used now the heads method on the data frame. Yeah, so it's a nice way to check the data. So in here, data refers to our pandas data frame. And then I apply here the head method and I print this off. And that just gives me an impression about, okay, did it work? Does the structure make sense? And it looks fine. So we have here the date. So this is our index. And in here, we have the different tickers, and then we have our daily log return. So it looks pretty good. Yeah, that looks acceptable. And it's limited to 5 rows. It's only the first 5 observations. It just is nice to check whether the structure is correct. And now we also have it stored in assets.csv. So here we can inspect the data. This is why it's kind of nice to use CSV files, because now we can just look at the data, so we can see all the log returns. So this was now a live download from Yahoo Finance. Yeah, and it goes back by 1 year. Of course, you have trading days, so certain days you might not have the data. So that looks all nice. So now we basically have done the first bit, and we have our data. And most importantly, I notice it is for free, which is great. In portfolio theory, and this is what we tend to teach in our undergrads, portfolio theory, also on master level courses, we now focus on mean variance optimization. So the key question is, now we have all these different assets, including gold prices and cryptocurrency. How do we combine these assets in an optimal manner? Actually, what does optimal mean? Well, there are 2 different things here. First of all, obviously, we want to make money. So we want to have a very high return. So ideally, the highest return possible. However, at the same time, we have to mitigate risk. So we try to find portfolios that have the lowest risk possible. So these 2 things are relevant, and there tends to be a risk-return trade-off. So usually, if an asset delivers a high expected return, you end up with a high variance, a high risk. Now, we use variance as a measure. We also use the standard deviation, which is the square root of the variance. We also call it volatility if we refer to the standard deviation of log returns. Yeah, so this might be a bit confusing if you're not used to finance terminology. Now, this is an example, and you will see that in live in a minute, where we calculate expected returns and we look at the standard deviation. So that's basically the volatility I mentioned. And under normal circumstances, you would expect, which is actually true for most time periods, that if your standard deviation goes up, your expected return tends to go up. But in this particular period, some assets performed really, really poorly. The worst performer here in the corner is United Health Group. Yeah, so this is a big insurance company. And this is mainly triggered by recent changes in the US in terms of health insurance provided by the state, which really massively affected their outlook in terms of profitability. And also you have quite a few other poor performers here, including also Bitcoin. Bitcoin didn't do too well. Of course, before that we had a rally. The big winner here is definitely gold in this period. That's up here. So that looks very promising. But again, when you do these calculations, the main thing is it always depends on your time period. And the issue with expected returns is what you tend to do is you look at these historical returns. Whether these historical returns are a good indication for the future, I would question this very much. And that's the problem you have in mean variance optimization, or shall we say one of the problems. So now what we do is we dive into Python and we do this optimization. using the CVXPY package, which is nice. It can do all the number crunching for us. And basically what we do is we maximize expected returns for a given level of risk, or we minimize risk for a given expected return. So basically this will move us to what we call in finance an efficient frontier. As I mentioned before, there are many alternative packages. So PyPortfolioOpt is an alternative, which is fine. But I think if you learn CVXPy, it's useful because it can be used in all settings of optimization problems. So it's very, very general. So once we derive efficient frontiers, we can then, of course, select one of these portfolios, but this selection depends on our own risk preference. So basically, the efficient frontier highlights this risk-return trade-off. So that's basically the idea. By default, to derive the efficient frontier, you will also derive the minimum variance portfolio, because that's the point where the frontier starts. So it is already a risk-based portfolio. So that is the portfolio with the lowest possible risk measured by variance. Let's look into this session 2 example. And let's jump up. So now it gets a little bit more complicated, as you might expect. So here we do now our usual import statements. We have NumPy, we have pandas, we have matplotlib.pyplot for data visualization. Again, one of many options. And then we use and import this CVXPy. And we also use our own function. Now you notice I also imported a second function, and I quite like to do this explicitly here, which is called moments. So moments basically calculates moments, so that this is the mean, the variance of various assets. And this is what we use as an input for the optimization process. So when we go to portfolio functions, you see our own function called moments. And moments as an argument takes df, which is a data frame. I assume it's log returns. Well, I know it should be log returns because we use the download function before, which returns the log return data frame. And then I also use trading days. So here I set the default 252, which makes sense for most markets. You can, of course, modify this, but that is, as you can see, an option. You don't have to. Yeah, so it takes default values. And you return many different things. First, a list which contains the names of securities. We only use that basically for labeling. Then we return the number of assets, so that should be an integer. We return expected returns, so these are the expected returns calculated based on historical data. And the expected returns will be stored in an array. So for our mathematicians, this is basically a vector. Yeah, but of course in computer science terms, we call it all arrays. Then we have the covariance matrix. So that is sigma. Again, it's another array or a matrix. So the covariance matrix simply calculates the covariance between all the different assets. And the covariance with the asset itself is, of course, by default, the variance. So if you look at the main diagonal of the sigma array, you basically find the variance of a respective asset. If you take the square root of the variance, you get the standard deviation. And this is what we will use later. And then the trading days, we need this for calculating basically annualized rates. Yeah, that's actually optional. You don't necessarily have to do it. It would also work. It's just for the purpose of displaying this and standardizing it. So in here, We use built-in functions. So we, of course, operate here on a pandas data frame, so we can work in pandas. We use the mean method. This will give us the averages. And then we use the covariance method. So this will give us basically the desired covariance matrix. And then you notice that the assets, so this is also returned, refers to the columns of the data frame, because we already designed it in this way that the data frame contains the ticker symbols as the heading for respective columns. And the toList method is a nice method where I can just put this into a list. And then I use the len function to know how many assets are there. Yeah, it's one way to do it. And finally, we then put it all together and focus here, you see that on the so-called attribute values. So again, if you're used to pandas, you will have seen this before. So dot values gives me the attribute, and this basically provides the NumPy array. So computationally, this is an efficient way of doing it. Yeah, so the log, you might have also seen the ilog, is a way to locate the respective series you want to look at. And we do it now based on our assets. Yeah, assets again is our list. Yeah, so that's basically giving us the right labeling and structure. And then we return the trading days, the list of assets, number of assets, the expected values, and the covariance matrix. Yeah, so that's basically how this works. So it's our own function. We just wrote this. And now, of course, you can download the data. We already have done this. So we can just now use our downloaded data in line 12 using the read_CSV function in pandas. And this will provide then our pandas data frame, which we name data. Again, we check the structure. It's always a good idea to do this just to make sure it kind of works. Then here you see we obtain now the moments. We call the function and we put all the different outputs in one line of code, which is pretty efficient. And then you can visualize it if you wish, or you can just print out the main parameters. I think I'll do both in this case. So in here, we use an enumerate. So that's, of course, a loop where we look at all the assets. We use the index to basically identify the expected value, which is stored in our array. And we also use it to identify the square root of the respective main diagonal entry. So that is our volatility. And we can just print this out. And here you notice in front of my quotation marks, I have F. So this is a formatted string where I can use these placeholder, these curly brackets to basically put in my variables. I use here a fixed format with 3 decimals. Otherwise, it's not necessary to go into all the further decimals. This is not necessary at all. Good, and then we can calculate, of course, standard deviations or volatilities. We can do it using the diagonal function in NumPy. So this is just storing volatilities. And we can then put expected return volatility into a data frame, which we then can use also to visualize it. Yeah, so that's basically what we do. And we can use the list of assets to label. That's fundamentally what comes in the next loop. So this is the annotation. So this will give us the same figure we just saw on the PowerPoint. And then we actually do the optimization. And so this now relies on the Python package. There are, of course, every package is a bit different, so you have to always, check out how it works. So in this case, we have to introduce a variable which provides basically a kind of a container for our optimization. and it will depend on how many assets are there. So I refer to the number of assets in the argument. So this would create basically an instance of the variable class, which is a class which is written in this Python library. And then for comparison, and this is in particular if you want to compare using also the Sharpe ratio, you need the risk-free rate. Now, the risk-free rate, and this is talking as a practitioner as well, tends to be a US government bond. Of course, now you might argue, is it risk-free? Well, fingers crossed it is. If not, we are in big trouble. So usually you take the yield of a 10-year US government bond. It should be around 4%, 4 to 5%. I put here 4.2%. But of course, you can always update that. Then the next two lines are interesting. I'm not sure whether you have seen this before. So there are different ways now of matrix multiplications in Python. So you can, of course, use in NumPy the dot product. So you could do something like NP dot, and then you would refer to your mu, so this is your expected return vector, and your x, which is your portfolio weights. Or you can use this operator, which does the same. It is, in my view, faster. Yeah. The next thing is basically the portfolio variance. So if you do this in finance theory, it would be the x transpose times your covariance matrix times x. The x transpose means that you move from a column vector to a row vector, and this will give you a scalar. So it will be 1 times 1 dimensional because the portfolio variance is simply a number. Now in Python, it's a little bit different because Python is very flexible when it comes to row and column vectors. It would treat these the same because these are arrays that have the size n, but they don't have a second dimension. So Python would just do exactly this calculation, but you don't need to do any transpose here. It would just treat this as a row vector. Just a little note. Then actually, this line does all the optimization for us. And this is pretty nice because it's, in my view, very intuitive compared to many other libraries I have seen in Python. So here we use the problem class. So this is the main class in CVXPY. We do a minimization. What do we want to minimize? So what's the objective function? We want to minimize our risk. Subject to, these are the conditions, and you see it's specified here in a list. So there are multiple things to consider. The first thing to note is that all the portfolio weights have to add up to 1. Now this is important because it means that we have to be fully invested. So we don't have any cash holding here. Then we also specify that the return, so our portfolio return, has to be at least the risk-free rate. So this cuts out the inefficient part of the allocation because it doesn't make sense to have a return below the risk-free rate that is based on a risky portfolio. That doesn't make sense. It's not efficient. And then we also specify that portfolio weights have to be positive. Yeah, not strictly, but positive. So this basically means no short selling. And then we solve the optimization problem and simply calling the solve method. And then I just print it out. That's what I do. I do a print out and we see how this looks like. So the next thing is basically just printing out the assets, have a look at what's in it, what's not in it. And again, it's the minimum variance portfolio. So we just now run this. So we went through the code in detail and we just give this a go. These optimizations can take a little bit of time, particularly depends on how substantial your data set is. So you have to be a bit patient. Also, any figures you do, they also might take a little bit of time. So of course, now this is done based on our current data. And of course, things already have moved a little bit compared to the figure you saw on PowerPoint. But fundamentally, it is similar compared to what we have seen before. So some poor performers, in particular also Bitcoin, but otherwise it's quite similar. So now we can look into what is included in our minimum risk portfolio. So this is the minimum variance portfolio. And we also have the individual measures of volatility and performance. Yeah, gold actually did really well, quite high return. Of course, significant risk, but still in relative terms, I think it did exceptionally well. And in the minimum variance portfolio, this would be my composition. And it might surprise you that in the minimum variance portfolio, we actually put in Bitcoin as well. And we put in gold. Well, of course, gold performed really well, but it's interesting. The main reason why you see that happening is because they move against markets quite a bit, in particular in this last period. So sometimes the composition of the portfolio might be initially a little bit counterintuitive because some weak performers might be in there, but they're in there because they offer an insurance policy, because they are less correlated with other assets. So this diversification benefit might be attractive. And you see actually our minimum variance portfolio has a volatility of only 10%, which is pretty good, and almost 20% return. Again, this is annualized. So that is actually pretty damn good, honestly speaking. When you look at individual assets, you have significantly higher risk to take. Yeah, so that basically illustrates the benefit of diversification. So that's all kind of nice and useful, but of course there are big limitations when it comes to mean variance optimization. So in theory, it is nice, it works. In practice, it really doesn't, and there are many reasons for this. So one reason is in reality, when you actually look at financial data are not at all close to what you call a log normal distribution. And in finance theory, we assume that the assets follow a log normal distribution. So the log returns would be normally distributed. In reality, you have significant outliers, so significant, extreme observations, either very high returns or very low returns. So you have so-called tail risk, which is not captured in this theory. But if you actually invest, that matters. Then, of course, the issue is that nothing is constant. Yeah, so your volatilities change over time. Yeah, so there are certain patterns, certain so-called volatility clusters. Correlations between assets also change. And in particular, you will notice this in the case of a crisis, because all of a sudden the correlations tend to go up. And this is a problem because your diversification benefit is not there in a crisis. And it is also really difficult to estimate the expected returns. Yeah, so what we do here and what's common is to use historical data, but there is no guarantee that historical performance tells me much about future performance. Yeah, so that is a major limitation. So what's the alternative? The alternative, which I've seen more and more done in practice, is to actually move away from mean variance optimization and focus only on risk, because the covariance matrix tends to be more stable compared to expected returns. And also when it comes to statistical methods in terms of forecasting variances and also correlations, which can be done, tends to be more successful compared to forecasting expected returns. It's just an empirical fact. So this is why these risk-based portfolios have become actually quite an active field of applied research. There isn't that much academic literature on it, in my view, but we will see. So I think it's worth exploring. So if you're interested in that, drop me a line. There's more to do. There are many different types of these risk-based portfolios. So there are, for instance, there is the equal risk contribution. So the idea is that every asset should contribute the same risk to the portfolio. So that's one way to do it. Then there's the maximum diversification portfolio. Now this is the one we look into because that's the most common one you see in practice. The maximum diversification portfolio tries to maximize the exposure to different sources of risk. So that is the idea. So what you do is you take the weighted sum of the volatilities of all the individual assets, and you divide by the volatility of the portfolio. If a portfolio is well diversified, the volatility of a portfolio will be much smaller compared to the sum of the individual assets volatility, and then you have a very high ratio, a high diversification ratio. So that's the idea, is you're exposed to many different sources of risk. And that's fundamentally now what we try to do in Python. And you will see in Python, this is again done very conveniently. We don't have to do much work ourselves. We just leave it to Python to do the work for us. Let's jump into this. So in here, we now derive our maximum diversification portfolio, or MDP. We do the usual imports. There is one more thing we do. We also import here spicy. So this is used for optimization in general. I use it in particular now if I want to modify here objective functions. And then I add some more functions to it. Now, of course, you can say, and you're absolutely correct to say this, why don't you also put this into portfolio functions and import these? And the answer is yes, I could, and it would be nicer. Yes, and you see, one should maybe refactor this code. Yeah, but as always, when you work on projects, so usually what happens is you start coding, and it runs, which is great, and then there are no big mistakes, which is even better. And then you optimize your code, and over time it will get better and better. And for instance, this here, these functions I would now actually outsource. Yeah, so I would put this in a separate script and then import, because it is a better idea. So this is not nice, but you know, it's good actually as a practice for you to see it. So portfolio statistics, what it does is it takes my portfolio weights. So this comes from the optimization. It takes the risk-free rate, which I need to calculate Sharpe ratios. So here we use a default of 4.2%. And then it calculates portfolio statistics. So here we calculate the portfolio return, which is simply the dot product of portfolio weights and the expected returns captured in our vector or array. And then we calculate the portfolio variance, or in this case, actually the volatility. We do the square root of it. And again, it takes here the portfolio variance from our previous calculation. And then we have the Sharpe ratio. This is a very common ratio to compare portfolios. So we look at the portfolio return in comparison to the risk-free return. So compared to taking no risk at all. And then we divide by the volatility of the portfolio. So put differently, how much excess return do you get for the risk you take? So that's basically the Sharpe ratio. So that's useful for comparison of portfolios. And then here we use a different objective function in our optimization. So this is the max diversification portfolio, which looks at diversification ratios. Yeah, so that's a different way. So we don't want to minimize risk for a given return. We want to maximize our diversification ratio. So being exposed to as many different sources of risk as possible. So again, here you see the portfolio volatility. And then here we have the sum of each asset's weight multiplied by its volatility. Yeah, you see that here. This comes from the main diagonal of the covariance matrix. And then we just take this ratio. You notice that I put a minus in front because our optimization in this setting is a minimization problem. So if I want to minimize something negative, I actually maximize it. So this is a common trick. Yeah, so you can always use a minimization algorithm, and you put a minus in front of your target function, of your objective function, and it will do actually a maximization. So as I said, it would be nicer to actually outsource these functions. So that can be easily done. Copy paste this and import. It would just work fine. So again, what we do is we load our data from the CSV file. We look at the data structure. We derive our moments. So this uses the same moment function. And then the optimization is a little bit different compared to what we have seen before. It's just a nice way to get exposed to different ways of optimization in Python. So here we specify the boundary conditions and the constraints. But in fact, it is very similar to what we have seen before. So here the boundary conditions we have refers to the minimum weight, which is 0, the maximum weight, which is 1. So basically what this does is it again removes the option of short selling. So you can't do short selling. So it's similar compared to what you have seen in the other optimization, just a different way of writing it. I think this way is a little bit more complicated also because you use here the lambda function, which is little bit more complicated to use compared to what you have seen before. But basically what this tells me is that the sum of the weights has to be equal to 1. That's the same logic here. Yeah. And then we have here the portfolio. This is our maximum diversification portfolio. So we start here with initial values. So you have to be a little bit more explicit here. So the thing is, what's a good starting value for an algorithm? There is no obvious reason. You can always take random values as long as you are inside these bounds. That would be fine. What I have done here is I simply start with an equally weighted portfolio. And this is a common approach. It comes more from Bayesian statistics because the argument is if you know nothing, you just do all of it in equal proportion. So basically the idea of a so-called flat prior distribution. But of course, this you can modify. Initial values can be important for optimization problems. So if you select not a good starting point, you might end up in problems. It might not actually converge. Yeah, so that can be an issue. Good. When we do the minimization, we use the bounds, we use the constraints. And then we basically obtain here the attribute. Yeah, so .x is the attribute, which basically gives me the portfolio weights. So you see it runs a bit different compared to the mean variance optimization we have seen before. And then we obtain the portfolio statistics, which gives me the expected return, the volatility of the portfolio, and also the Sharpe ratio. And we just now print it out. So that's basically what we do. And this is for our maximum diversification portfolio. Let's just now run this. So we can go back like this. And now we are script number 3 and we run it. And it does now do some more number crunching, so it might take a while. And it finds now the portfolio that is optimal in terms of maximum exposure to different sources of risk. Good, so the data looks fine, and then this is our outcome. Yeah, so this is our actual return, our volatility. The return is pretty bad, and the Sharpe ratio is even worse. Yeah, so that basically tells you that using maximum diversification portfolios might be an interesting idea from a risk perspective, but in the past, so based on this data set past year, the return looked pretty much awful. Yeah, so you would have been better off just putting the money into US government bonds. Yeah, so that's the thing. You always have to test. Yeah, so don't just implement something and assume it's always amazing. It is not necessarily the case. Good. That now moves us to an important aspect of anything you do in terms of portfolio optimization. You always have to test, test, test. There is absolutely no guarantee that one method always works. It depends on market conditions. And as I mentioned before, sadly, in financial markets, none of these parameters are the same. They keep changing. So you have to think about also how you reallocate a portfolio. The problem in particular, when it comes to using now historical data for this testing, is that for us, the time series matters. So the so-called temporal order matters. So what you cannot do is you cannot mix up future and past observations. So that happens a lot if you come from a computer science, machine learning, AI background. Because in these areas, it's very, very common to use built-in functions that split training and testing data, and they do this randomly. There might be stratification in place in the case of classification problems. But a random allocation of observations would destroy the temporal order. Because in principle, if I do a random resample, I could pick future values and put it back. And this is not really making much sense if you have time series data. So one has to be really careful here when it comes to backtesting with financial time series, because that would not work. And there are lots of issues when it comes to also deriving optimal portfolios, because by accident, you might end up getting future information into your optimization. In particular, this happens if you use machine learning tools, because most of these tools are not made for time series. They do not actually, understand the data structure. Yeah, you have to use so-called feature engineering to convert time series data into supervised machine learning data. And this can be very, very tricky, and you might end up with significant mistakes. So backtesting is a huge topic. So we will look into this. We do something quite simple to start with, and we think about actually what we have done and what better ways are there. There is more to say in particular about using a static portfolio and using a dynamic approach. So of course, in practice, if parameters change, so if the variances shift, if correlations shift, you might change your composition of your portfolio. The key question is, how many times do you adjust? Because any adjustment also triggers transaction costs. Yeah, so when you run these simulations, you would then have a trade-off between, too frequent adjustments and high costs, and maybe better performance. So that's something you have to really work out. So backtesting in our case is, first of all, very simple. We use only now the historical data in the beginning, and we also do something else. We throw in one additional risk-based portfolio, the so-called Eigen portfolio. Now, the Eigen portfolios recently, I would say they got more and more attention. Now, what's the idea of the Eigen portfolio? It's actually based on unsupervised machine learning. So the idea is to look at all the different assets, and you construct by using actually principal component analysis, so basically factor analysis, you construct an optimal portfolio that is optimal in the sense of capturing the most variance possible. So that's basically what it does. And it constructs multiple Eigen portfolios. And the important feature is that these Eigen portfolios, by construction, because these are the so-called principal components, they are uncorrelated. So they give you by default a different exposure because correlation is by construction 0. The Eigen portfolio, the first one in theory, should be similar to a market portfolio. Now, in finance theory, we always use the market portfolio as a reference point. So if we talk about the capital asset pricing model and so on, we use market portfolios. The tricky thing is market portfolios are not necessarily easy to observe. You can argue if you are in a developed stock market, I just use the main stock market index and it should be fine. But of course, a stock market index does not capture all the assets in an economy. It doesn't. In particular, in emerging markets, this can be quite tricky, and it can be very tricky in particular when to use these stock market indices for calculations like, estimating the so-called beta coefficient, which you need for cost of equity estimations and finally also for firm valuations. So an alternative way is to use Eigen portfolios, and I will show you this in Python, and we can have a little look how this behaves. So here we are. So it's getting a little bit more complicated. We have the same function. We spoke about this max diversification, and now I also threw in here the minimum variance, but we already have seen minimum variance before. It just is as an objective function the variance of the portfolio, and it's a minimization problem, so that's fine. And now we have the Eigen portfolio. So this is new. The Eigen portfolio is basically a decomposition of my covariance or correlation matrix into the respective eigenvectors and associated eigenvalues. Now, this might sound a bit outlandish, but actually what it does is what you see in so-called principal component analysis. That's basically what it does. So you can always decompose a covariance matrix into its respective eigenvectors, and they basically can be used when they're used in machine learning in particular to reduce the dimensions of a data set. To basically, it's like a projection from a higher dimensional space to a lower dimensional space, which can be useful for interpretation purpose, but also for running algorithms on it, because you need fewer variables, fewer dimensions, and it can be computationally beneficial without losing much information. So that's basically behind it. But you see this linear algebra package goes back to NumPy. It's box standard. Yeah, so that's basically what we tend to do. You also then tend to do a normalization of these eigenvectors, which again is a standard approach. And then we return these eigenvalues, eigenvectors, or eigenportfolios, and we only use the first one because that is kind of like a market portfolio. Then we follow the same logic as before. Yeah, same constraints as before. And then we run through the different types of portfolios. So here we have a maximum diversification portfolio. We have the, should be actually minimum, not maximum. Yeah, so minimum variance portfolio. And then we have the Eigen portfolio, which refers to the first Eigen portfolio. Yeah, this just comes out of our decomposition of the covariance matrix. And then we compare them in terms of return, volatility, and Sharpe ratio. So that's basically what we do. So we now just run this and see actually who will be the winner. Now that's a bit more calculation time. Here we are. Okay, so in terms of what we have done, we already know the maximum diversification portfolio doesn't do very well in this period. It certainly doesn't. It's terrible. Minimum variance, looks promising. So volatility is indeed, as expected, the lowest. It has a really decent return for that. The Sharpe ratio is pretty damn impressive. The Eigen portfolio didn't do very well in comparison. Yeah, so if you look here at volatility, you have a higher risk. Return is not any better. It's actually worse. Sharpe ratio pretty much not impressive. However, there is one big catch here, and the catch is actually in our code. Yeah, so when we do this type of optimization and compare these portfolios, we basically use data for the whole period. So we basically do an optimization looking back and assuming we know everything up to the current point. Now, this, of course, is not realistic. So what you should do is you also should look at so-called out-of-sample performance. So the idea is the following. You restrict information. You just basically get rid of some of the information, which you will actually do in the optimization part. So here, when you derive the moments, you basically restrict in here using slicing the access to the data. So what you do is you cut off the last bit, which I call now M. Yeah, so you basically only take data up to a certain point, and you use that to derive optimal portfolios, and then you see the performance in the time period, which is not part of your information set. So basically you can say, let's stop maybe 30 days before the end of the period, optimize our portfolios, and then see what's the performance for the next 30 days. And this gives you a proper out-of-sample performance. So that is better. And that is what I have done in the next one, which I also have to upload to GitHub. So exactly that's the logic. So here we have an out-of-sample period, which I just call f_underscore period. I put in 30 days. Yeah, you can of course modify this. And now you see in terms of slicing, I go -30. So the last 30 days are cut out. We don't know it, then we do the optimization. Then I run the optimization for the different portfolios, and then I assess the portfolios based on the period which hasn't been covered. So I start 30 days before the end of my period, and I go to the end. You see this here in slicing. So that is an out-of-sample property. So now I compare these portfolios in the last 30 days, assuming that we didn't know about it. Yeah, so this is proper assessment of out-of-sample properties. This in finance is useful, and it's important because we did not mess about the temporal order of our financial time series. And we just now run this and see who the winner will be. Let's see. I haven't done it, of course, but this is different data, so I will be excited to see that. So here we go. So now it is actually a little bit different. Yeah. So again, maximum diversification performs poorly. So if we restrict us to information before the last 30 days, do the optimization, it still performs really, really badly. So nothing you would really recommend. Minimum variance is doing again pretty well, honestly speaking. And the Eigen portfolio is now doing a lot better. But now you see something really interesting. Look at this minimum variance portfolio. It is no longer really minimum variance. And this is because parameters changed in the last 30 days. Yeah. So we optimized the minimum variance portfolio based on our information we had at the time of investing in the portfolio, which was 30 days before. Then we invested accordingly, and then we wait for 30 days and we see what's the actual performance. And as you can see, the minimum variance portfolio was not really minimum variance, but it at least delivered a really good return, and the Sharpe ratio is pretty amazing. The Eigen portfolio did actually better in terms of risk. And that's exactly the problem you have in portfolio optimization, because let's face it, in financial markets, things keep changing. And this is not done, of course, on 30 days. You can take shorter periods, you can take longer periods, and you will see more serious deviations. But in summary, risk-based portfolios are interesting. They are used in practice, and I think they are an interesting option to explore. Now, this is basically what I wanted to cover. We have another 14-15 minutes or so, so I will stop here. If you want, there is a lot more to explore, so you can always find me on LinkedIn. I'm more than happy if you send me a message. I tend to respond quite quickly. You'll find us on Unicorn with free content around data science, finance. There are a few Udemy courses which I will update this year on time series modeling, but using Starter, and on company valuation using Excel, because this is what you do in company valuation. There's a 365 data science course on econometrics using Python, which actually was really well put together. It's an amazing team at 365 Data Science. They did a great job with all the animations. It's really fun. I think about 1,700 people actually have done this course, so that's pretty cool. And then we do a new one on advanced machine learning AI applications in finance. This will also contain this part around risk-based portfolios and much more using machine learning tools. We go more into forecasting, we do random forests, we do neural networks, and so on with financial data, and much more on backtesting. So this course should be available soon. We are currently working on this, and yeah, hopefully it's also fun to do. And then I do a project with Starweaver on an IBM course, which should be also available soon, in the next months, I guess. Again, we are currently working on the animations and the fun bits. So that's basically what I wanted to cover. I will now stop sharing, and I'm happy to take any questions if there are any. And of course, if you have some questions later, feel free to get in touch. I'm more than happy to have a discussion. So we have some Q&A. Of course, before that, I can't see it when I'm sharing. Yeah, so feel free to.
Hi, everyone. Yeah, hi, Gerhard. Just a request, if you have any such questions, please feel free to ask and put it into the Q&A box.
You can also shout out, that should be fine as well. I just put my link to my GitHub. Anyway, once you are on GitHub, you have links to all the materials. So that's usually for me, the best way to navigate. So that's here the link to GitHub. Yeah, on GitHub, you have actually all the stuff you need. And also we have here the website as well, which also has all the links. So if for various materials, I think this should be this one here. It should also be fine. So that's our main website. The interesting thing is, when I moved from academia to McKinsey, I kind of assumed I would need more of my finance knowledge, but actually that wasn't really true, because really in practice, finance theory had really very little impact in consulting. The only thing I really needed was very, very good skills in Excel. Funny enough, there wasn't much programming going on back then. So we did only really basic stuff like correlations, regressions, using Excel mostly. So when I started using some other things in Starter or so, that was a bit outlandish. And back then, Python wasn't yet very common. Yeah, so that's of course a thing. This came in, of course, a little bit later, and then it became really big. And of course, now the big question is what happens in future? Will it be always, Python? I don't think so. I think it will be different, most likely. And of course, also one should not ignore now other developments, in particular around C# in certain applications, which are quite interesting as well. So you never quite know, and you have to keep updating, in my view, and yeah, keep learning, because things keep changing an awful lot. Yeah, so if there are any questions, let me know. Oh, I just see Julian, my friend, is here as well. Greetings. Yeah, otherwise, of course, you find me on YouTube, on LinkedIn, and feel free to have a chat. There is more to come now in terms of, in particular, simulations I want to do. So this is current research work I do. And of course, again, you might say, why do you need to simulate data? You have so much in terms of data, but certain things we actually can't observe. Yeah, so stuff like supply chains, for instance, it's not public data. So if you want to model a disruption of supply chains due to, say, geopolitical risk or sanctions, anything like this, it's not at all straightforward because you don't have the data in public. So this is true for many problems. So I think I will do more on that using SymPy, which is a pretty cool package as well. Yeah, why not max sharp instead of MVP? Absolutely, you can do that. You can maximize the sharp ratio. In fact, this is what you do in terms of getting the so-called tangent portfolio. The problem with the sharp ratio is well, it's twofold. Number one, for the sharp ratio, you have to understand the expected returns. So you're back when it comes to the problem how to predict expected returns, and this tends to be a little bit tricky. And also you have to, of course, obtain the risk-free rate. And again, this is sometimes a little bit debatable. In particular, given the significant geopolitical risk at the moment, given also the fact that you have quite high inflation, lots of uncertainty. So that makes it sometimes a little bit tricky. And many people also criticize the Sharpe ratio as well. So there are, why is only the portfolio volatility the right measure? Because sometimes you might have significant tail risk, which is not captured. Fair enough. And so there are many other measures you can use. But yes, it's used as well, and there are good reasons for it. But it does not fix, of course, certain problems. So the main challenge in practice is that, unfortunately, all of these parameters, as you have seen also with the out-of-sample performance, they keep changing. So you might assume you are in a low-risk portfolio, but all of a sudden, actually, you aren't. And that makes it really so difficult. And also the belief that somehow with machine learning AI tools, all of a sudden it will be just our predictions will be just better is highly doubtful. That's the problem. Because why? If everyone is using the same AI machine learning tools and everyone has better predictions, will the outcome be a more predictable market? I doubt it very much. There's one important counter argument in particular. If it's convenient to use AI and machine learning tools, nobody does actual research, in terms of understanding fundamental values. And maybe then the information you obtain from observing the prices might be less reliable. So that's basically also the content creation argument as well, because if AI is using content created by content creators without paying them, there's no incentive to create content. And at the end of the day, you have AI feeding on AI in future. And you see this a lot now on YouTube, of course, as a YouTuber. You get a lot of, I talk a lot to other YouTubers about this, all these AI channels popping up, where you can in seconds generate content. But of course, yeah, it undermines real creativity. And so we will see how this develops. Yeah, but it's not at all straightforward. Yeah, so if any further questions, let me know. Yeah, otherwise, it's time for lunch, at least for me. So I just wonder, खाना में क्या है?
I guess we are not having any further questions as of now. And as Gerhard have said, that is bringing us towards the end of the workshop. I believe and I hope that all of you have had this enlightening session and you would learn from it. What exactly, and apart from that, I really want to thank Gerhard for sharing his expertise with us and for making these complex concepts and topics accessible and, making use of practicality. The passion and Gerhard, your passion for both finance and programming really came through, and it was a fruitful session. For those of you who want to dive deeper, remember that all the materials, as Gerhard has mentioned, are available on his GitHub. The links have been attached. I encourage you to explore his other repositories as well. And thank you again to all for your active participation and the questions which you have been asking throughout the session. I'll be seeing you at the other free workshops which Pact keeps organizing every such week. Recordings, as far as concerned, will be shared on your email addresses once the session is over in the next 24 hours. Until then, stay healthy, eat healthy, keep practicing, and have a nice day ahead. Thank you, everyone. Thank you, Gerhard.
Thank you. Thanks for organizing. Take care.
Bye-bye. Take care. Bye, everyone. Bye. Take care.